This video is about the multiple linear regression, also known as the multivariate linear regression. In the multiple or multivariate linear regression, there are now 1, 2, up to p number of predictors that are correlated with y. Let's consider some assumptions. Just like the simple linear regression, one assumption in multiple linear regression is that the residuals, which is represented by the error term here, are normally distributed. An additional assumption in multiple linear regression is that the predictors, in this case x sub 1, x sub 2, up to x sub p, are independent. Or in other words, they must not be correlated with each other. So let's open the file bloodled.r data. So this is about a group of researchers who wanted to determine the factors that contribute to the amount of blood lead level in radiator repair workers. They gathered data such as the number of radiators repaired per day, the number of years being employed as radiator repair worker, and some renal function tests such as the FBS, creatinine, BUN, presence of protein in urine, and the eGFR. Conduct a multiple regression model to determine the factors that contribute to the amount of blood lead level in radiator repair workers. Use 5% level of significance. So given this data, we're going to predict y, in which y is blood lead, which is beta sub 0 plus beta 1 x1. x1 may be the number of radiators repaired per day, which is represented by this, plus beta 2 x sub 2. x sub 2 may be the number of years of employment, up to beta sub 7 x7, since we have 7 predictors here, plus the epsilon. Now, consider here that we're going to make use of a linear regression model since y is a quantity. Remember that linear regression is used when y is a quantitative variable, specifically a continuous variable, meaning decimals are allowed. Before we proceed, I would like to clarify that one of the predictors here is a categorical variable, meaning it's coded here that 1 means there is a protein in urine and 0 means there is no protein in urine. Other variables are quantities. So FBS, creatinine, BUN, eGFR, number of radiators, and years of employment are all quantities. Now, let's open the data, bloodled.r data. So we may take a look at the data by typing the name, bloodled. And here we see the 27 samples or the 27 radiator repair workers. So we have the ID, the bloodled, the number of radiators, the FBS, creatinine, BUN, protein, which is 0 and 1, eGFR, and years employed. Now, let's perform a linear regression using the LM function followed by your dependent variable y, which is lead, and all of this are the predictors. Then don't forget the file name. So let's name it as bloodled reg. Then press enter. Then we may see the result by typing blood reg or summary bloodled reg. So here's the result of the multivariate or the multiple linear regression model using lead as the dependent variable. Let's start interpreting the results. Let's start with the r squared. Now, in the simple linear regression, we are interpreting the multiple r squared, which is the square of the Pearson r. Now, in the multiple linear regression, it's not wise to interpret this one. because mathematically, multiple r squared increases as the number of predictors increases. So, the multiple r squared may be deceiving that it is high. It's not because of the contributions of x to y, but because there are many predictors. Now, what we do is, we interpret only the adjusted r squared when we have the multiple linear regression. Again, it's not wise to interpret multiple r squared because multiple r squared is a function of the number of predictors. The more predictors you have, the higher the multiple r squared, which is not good because the true r squared may be overestimated. So what we do is, we interpret the adjusted r squared. So the adjusted r squared is 0.802, which tells us that 80.2% of the variation in y, which is lead, is contributed by these predictors, in which the remaining 19.8% is due to errors or unknown. Again, note that adjusted r squared in use in replacement for the multiple r squared when p, or the number of predictors, is greater than 1. Or in other words, when conducting a multiple linear regression, use the adjusted r squared rather than the multiple r squared. Next, we have the ANOVA result. So since our linear regression model is that the blood lead is equal to the y-intercept beta 0 plus beta 1 x1, in which your x1 is the number of radiators, plus beta 2 x2, in which x2 may be, let's say, FBS, plus beta sub 3 x sub 3, in which x sub 3 is your creatinine, and so on until you have beta sub 7 x sub 7, in which your x sub 7 is, let's say, years employed, plus some epsilon. So in other words, this is your x1, x2, x3 up to x sub 7. Now, the ANOVA tests whether beta 1, beta 2, beta 3 up to beta sub 7 are all equal to 0. Now, if all the coefficients are 0, so meaning this is 0, this is 0, this is 0 up to this one, meaning y will be constant. Y will not change even if you change x1, x2, x3 up to x sub 7. So since these are 0 under the null hypothesis, then no matter how much you change x1 to x sub 7, y will be constant. Alternatively, your HA is, there is some, or there exists some coefficients which is not 0. Now, since the p-value here is less than 0.05, then we're going to reject the null hypothesis and claim that there's sufficient evidence that at least one coefficient is not 0, which is a good result. Okay? So, in ANOVA result here, you have to consider that a p-value less than 0.05 is a good result because there is a coefficient that is not 0, meaning you were able to find at least one predictor of y, in this case, blood lead. Note that when the p-value here is greater than 0.05, we're not going to reject the null. Then we claim that beta 1, beta 2 up to beta sub 7 is 0, meaning there is no predictor found for y, in this case, blood lead. Now, what are the predictors of blood lead? We're going to take a look now at these individual tests. Now, what are the predictors found? Again, our equation is beta sub 0, which is the y-intercept. Or in other words, we have y equals negative 1139.26. Next, we have beta sub 1, which is 1.6723 of x sub 1, whatever is the number of radiators, plus beta sub 2, which is 99.6967 x sub 2, and so on, until you have the last one, which is beta sub 7, which is 12.2398. times x sub 7, which is the years employed, plus some error term. Now, since the ANOVA tells us that there is at least one predictor found, we're going to test all the betas individually, starting with beta sub 1. So your null hypothesis here is that beta sub 1 is 0, alternative, beta sub 1 is not 0. And then take a look at the p-value, which is 0.803. Now, given that p-value, should we reject the null? Since it's greater than 0.05, then we're not going to reject the null. Meaning, we're going to conclude in favor of the null hypothesis, which tells us that there's a reason to believe that your beta 1 is 0. Or in other words, if you have this equation and x1 is your number of radiators, no matter how much you change here, beta 1 is 0, so it will not change y. Which goes to show that the number of radiators is not a predictor of blood lead. On the other hand, let's try FBS. So for FBS, so your null hypothesis here is beta sub 2 is 0 and beta sub 2 is not 0 for the alternative. Now, since the p-value is 0.312, again, we're not going to reject the null hypothesis. Meaning, we have a reason to believe that beta sub 2 is 0. Or in other words, when we get the population, there's a chance that beta sub 2 is 0. So we do not reject the null and claim that there's no evidence that beta 2 is not 0. So this tells us that likewise, FBS is not a predictor of blood lead. Now, which of the following here do you think is a contributor of blood lead? So since the null hypothesis is not rejected whenever the p-values are greater than 0.05, which of the following here is a predictor of blood lead? We see here that protein and years employed are the ones with p-value that's less than 0.05, indicating that the null hypothesis that their coefficient is 0 will be rejected. So this shows that protein and years employed are the predictors of blood lead, which indicates that 1 unit increase in years employed will increase the blood lead by 12.2398. Now, I'll show you more details in that interpretation. So suppose we want to estimate the blood lead level of a radiator repair worker with this information. So 5 as your number of radiators, 5.1 as the FBS, and so on. Meaning, if you have this linear regression equation, which is coming from this, the number of radiators will be 5, the FBS will be 5.1, creatinine will be 102, BUN will be 5, protein or proteinuria is 0 since that is negative, EGFR, which is 90, and years employed, which is 10. Substituting those values, our estimate of the blood lead level of that radiator repair worker is 108.74097 micrograms per deciliter. Next, suppose we want to estimate the blood lead level of another radiator repair worker having these values. So all we have to do is to substitute the same values with the values here. And we're going to get 120.98 micrograms per deciliter. Now, suppose another radiator repair worker has this information. So again, substituting the value, number of radiators as 5, FBS as 5.1, until of years of employed, which is 11, we're going to have 802.62977 micrograms per deciliter. Now, let's summarize those three estimates. So here is the first one, the second one, and the third one. And here are their blood lead estimates. Now, this participant and this participant have the same number of radiators, the same FBS, the same creatinine, the same BUN, the same proteinuria, the same eGFR. The only difference is the years if employed was increased from 10 to 11. And take a look at the increase in the blood lead level. From 108.7, it turned out to be 120.98. So this shows that when all of these are held constant, 1 year increase in the employment will increase the blood lead by 12.2398, which is simply the difference from 108.74097 to 120.98077. And that is actually the one being referred here. So this shows that when all other variables were held constant, 1 unit increase in this years of employment, or in other words, 1 year increase in employment, will increase the blood lead at an estimate of 12.2398. On the other hand, this participant and this participant also have the same information on number of radiators, FBS, creatinine, everything is the same. eGFR and years of employed, except that this participant has no proteinuria while this participant has proteinuria. And look at the blood lead level increase. From 120.98077, it increased to 802.62977, which is an increase of 681.649 micrograms per deciliter. So this shows that when a radiator repair workers is positive compared with negative, he has a blood lead level that is 681.649 higher as compared to those who do not have proteinuria. And this value is the one represented by this value here. So in other words, how do we interpret 681.649? When all other variables were held constant, 1 unit increase in this. However, there's no unit in protein since this is the presence or absence of proteinuria. 0 means absence, 1 means present. So 1 unit increase means that from absent to having proteinuria, or in other words, when a radiator repair worker has proteinuria, his blood lead level is 681.649 higher as compared to those without proteinuria. So to write the results, years of employment and proteinuria are the factors that contribute to the radiator repair workers' blood lead levels, which indicates that keeping other variables constant, 1 year increase in the employment, their blood lead levels increases at an estimate or average of 12.4, which is from this result. And the p-value here is the one represented by this. And moreover, the blood lead levels of radiator repair workers with proteinuria are 681.65, which is the one represented by this coefficient, higher compared to those who do not have proteinuria. Then don't forget the p-values are the one displayed in the results. And then, this one are the variables with p-values greater than 0.05, which are not evidently the contributing factors to radiator repair workers' blood lead levels. Let's have another example. Suppose we have colon cancer.r data. So let's open the file and take a look at the data. So type colon cancer. So we see here 18 participants or 18 patients with colon cancers. Their neutrophils, their lymphocytes, their red blood cell distribution width, which is RDW, and cancer antigen were measured. So the dependent variable here is the cancer antigen 15-3. So let's determine whether neutrophils, lymphocytes, and red blood cell distribution width are predictors of cancer antigen. We simply type LM and then the dependent variable and then the independent variables here. Then don't forget the file name. So here's the result of the multiple linear regression. So again, let's interpret the results here. For the R squared, we're not going to make use of the multiple R squared. Again, since this is a multiple linear regression, we're going to make use of the adjusted R squared, which tells us that 30.86% of the variation in the cancer antigen is contributed by the neutrophils, lymphocytes, and red blood cell distribution width. Now, the p-value here in the ANOVA, since that's less than 0.05, it tells us that there's at least one predictor found, which is a good result. Now, which of the following variables, neutrophils, lymphocytes, and RDW, are predictors of cancer antigen? So, all we have to do is to take a look at the predictor with p-value that's less than 0.05. And that is neutrophils and lymphocytes. And how do we interpret these two values? So note that the unit of measurement for neutrophils is times 10 raised to 9 per liter, and the unit for measurement of lymphocytes is percent, while the unit of measurement for cancer antigen is units per liter. So how do we interpret this? So 1 unit, which is 1 times 10 raised to 9 per liter, increase in the neutrophils decreases the cancer antigen by 426.57 units per liter. And 1% increase in the lymphocytes decreases the cancer antigen by 508.17 units per liter. Again, while keeping other variables held constant. Let's have the last one, which is call 0.R data. So let's try open the file and take a look at the data. So call 0. So in this case, I have 32 participants and whether they are smoker is recorded. So consider here that cholesterol is quantitative, which is measured in millimeters mercury. Weekly is also quantitative, which is expressed in Rs, while smoker is qualitative or categorical variable, in which 0 if he or she is a non-smoker and 1 if a smoker. Now what we want to do here is to build a regression model which will predict cholesterol. In this case, this is your Y and these are your X. Now, doing the regression model, all we have to do is to use this code. How do we interpret weekly exercise of negative 10.436? It indicates that 1 unit increase in weekly exercise, or in other words, for every 1 hour increase in weekly exercise, cholesterol decreases at an average by 10.44 millimeters of mercury, keeping other variable constant. Now, how do we interpret smoker? So 1 unit increase is like 0 and 1, meaning you're comparing non-smoker with smokers. So meaning smokers have cholesterol level which is 23.7 millimeters of mercury higher as compared to non-smokers. Now, what if, let's try to add a variable. So on call 1, I added race, in which 1 is Asian, 2 if black, 3 if white, and 4 if Hispanic. Let's try to come up a linear regression model using this data. So how do we interpret this? So 1 hour increase in weekly exercise will decrease the cholesterol level by 10.84 millimeters of mercury while keeping other variables constant. For smokers, so smokers have cholesterol level which is 22.1106 higher as compared to those who are non-smokers. Now, how do we interpret race, which is 5.28? So, the way we interpret the other variables is that 1 unit increase, like 1 hour increase in weekly exercise, changes the cholesterol by negative 10.84. 1 unit increase in smoker, meaning from non-smoker to smoker, will increase the cholesterol level by 22.11. Now, how about race, which is 5.28? Are we going to interpret it the same way, like smoker and weekly exercise? Like 1 unit increase will increase the cholesterol by 5.2. Like comparing black with Asian. So from Asian to being black, or from black to being white, or from white to being Hispanic, is that it? Actually, it's not. This is not the proper way of putting a linear regression model if you have a categorical variable with more than two outcomes like this one. So how are we going to deal with this? We have to add what we call a dummy variable. So a dummy variable are added to represent categorical responses. Like in this case, if we have race, this one, we're going to separate each possible response as another column. Like race for Asian, race if black, race if white, and if race is Hispanic. Now, if this is 3 indicating that that participant is white, then on the column which is race white, that's 1. The rest are 0. If this is 4, then he is Hispanic, meaning these 3 are 0 and this is 1. This is 3, so this is 0, this is 1, and 0. Now, how about this? This is 2, meaning it's black. So this is 0, this is 1, this is 0, and this is 0. How about this? This is an Asian, so 1. So this is 1, and then the rest are 0. So that's how you deal a dummy variable. Now, can we already proceed with a linear regression model out of this? Almost. But remember, since we already separated the race according to possible categories, we're not going to consider race anymore. So we're going to deal only with race 1, race 2, race 3, and race 4. However, note that in linear regression, one assumption is that the predictors must be independent. These variables are dependent with each other because this is 1 when everything else here is 0. This is 1 because these 3 are 0. So they are dependent with each other. Now, to make this independent, all we have to do is to remove one of them. Meaning the one that is removed, in this case being Asian, will serve as the reference. So in other words, it's like race being Asian will be 0, the rest of this will be 1 later. So our basis or reference will be being Asian. Because again, that's one that is removed. That's why it is 0. Now, all we have to do is to build a linear regression model using this data. So let's try to open call to point our data. Let's have summary and then this LM. And we will have this result, which is also the same if we put factor and then race. So this indicates that race is considered a factor or a categorical variable. So doing this, we're just going to have exactly the same result. Now let's interpret the results. So how do we interpret weekly exercise? So this tells us that 1 unit increase in weekly exercise or 1 hour increase in weekly exercise will decrease the cholesterol level by 10.4. And smokers have 22.5 millimeters of mercury higher as compared to non-smokers. Now, how do we interpret these three? Remember that these dummy variables are like your 1, in which your race being Asian, which was removed, is like your 0. Meaning, you're going to compare race 2 with race 1, race 3 with race 1, and race 4 with race 1. So, meaning, 4.5872 here indicates that, what's race 2? Black. Meaning, blacks have cholesterol which are 4.5872 higher as compared to Asians. Likewise, race 3 which is white. So whites have cholesterol level which are 4.99 higher as compared to, again, Asians. And race 4 which are Hispanic. So Hispanics have cholesterol which are 17.11 higher compared to Asians. So our basis will be Asian since that's the one that was removed. So that's how you deal with a dummy variables. Last, what if I add another column which is gym hours? And then I try to put a linear regression model out of this. Remember that predictors must be independent, meaning these variables must be independent. However, as we see, weekly exercise has something to do with gym hours. The more gym hours you have, the more weekly exercise that you have. If we try to take a look at their correlation, meaning I try to perform a Pearson R here, I will see that their correlation is 0.97, which is very high. So that indicates that these two are correlated, which violates this assumption. If we try to put a linear regression model out of it by adding gym hours in the model, this time using call-tree, what we're going to have is this result. However, take a look at that result compared to our result a while ago. Notice here that the weekly exercise coefficient changed from negative 10, and adding a variable which is gym hours, it has increased to negative 7.7. The coefficient for smokers did not change much, as well as the other three. However, there's a sudden change in the weekly increase, indicating that weekly exercise is affected by the additional variable. Now, in linear regression, since these are assumed to be independent, no matter what variable that you add, it must not change these coefficients dramatically. That's why in some journals, they present results which are univariate and multivariate just to check whether there's a dramatic change in the coefficient estimates. So again, since the addition of gym hours, which is correlated to weekly exercise, led to dramatic change in the coefficient of weekly exercise, the addition of gym hours in the model is incorrect. Thus, we should stick with the previous result wherein gym hours is not included in the model. So I'd like to show a study here which is the prediction of the induction to delivery time interval in vaginal labor, which is a retrospective study in a Chinese tertiary maternity hospital. So take a look at the table 5 here, which use a multiple linear regression in which the gestational age used dummy variables and this one served as a reference. So this indicates that the delivery time is higher by 2.1 when the gestational age is 39 to 41 weeks as compared to those with gestational age of less than 39 weeks. Likewise, the delivery time interval is higher by 2.906 when the gestational age is at least 41 weeks as compared to those with gestational age of less than 39 weeks. PROM here refers to the premature rupture of the membrane. It's a categorical variable, meaning if there is a premature rupture of the membrane, this is 1, and 0 means there's no premature rupture yet. So this means that when there's a premature rupture of the membrane, the delivery time interval decreases by 6.512. And the fetal weight here indicates that for every 1 kilo increase in the fetal weight, the delivery time increases by 4.099.